Alright, this problem is rather involved, so let's get to it. A massless hoop of radius r is free to rotate about its center in a vertical plane. A massless m is attached at one point, and a pendulum of length √2 r, and also of mass m, is attached at another point 90 degrees away, as shown in the figure. Let theta be the angle of the hoop relative to the position shown, and let alpha be the angle of the pendulum with respect to the vertical. Find the normal modes for small oscillations. Okay. First off, let's set our coordinates. So we'll have, that's plus y, that's plus x. And we'll set our origin to be at the center of the circle. So that's O. And we will set our theta to be sort of originating on this dashed line here. And it'll be increasing counterclockwise. So that's positive theta. And our alpha will also be positive counterclockwise. Okay, so we want to set up our Lagrangian for this system, and then we can use our Euler-Lagrange equations. So in order to do that, we need our displacement vectors, and then we can take some derivatives. So let's start with, I'll call this mass 1, this is mass 2. So let's say call it R1. Okay, so let's start with the x coordinate. So this magnitude here is going to be r sine of 45 initially, right? But imagine increasing theta to 45 degrees. Then that means that the m1 is going to be right here, and that means that our x coordinate is going to be 0, right, relative to the origin. So we're going to need some sort of dependence inside this function on theta. Also, m1 starts to the left, so we're going to have a minus r sine 45 plus or minus theta. But we need to figure out which one of these it is. So if theta is equal to 45, then let's say if we do plus, we did 45 plus 45, that's 90. Sine of 90 degrees is 1, so that's going to give us negative r, which we don't want. Remember, it's supposed to be 0. But if we do minus, then we'll have 45 minus 45, which is 0. Sine of 0 is 0. Boom. That's it. Now for the y-coordinate. So this length here is r cosine of 45 initially. And then imagine, again, rotating 45 degrees to this point. The y-coordinate is going to be minus r. So let's logic our way through this again. And of course we have this minus here because we're below the y-axis. Oops, this is supposed to be cosine. Okay, so if we did plus, we would get 45 plus 45, which is 90. Cos of 90 is 0. Do we want 0? No, we do not. If we did minus, we'd have 45 minus 45, which is 0. Cos of 0 is 1 times negative r gives us what we want. So then this is minus. Okay, and if in case you're still confused why we have this 45 business inside the argument, is because they told us theta is relative to the position shown. And so this theta is always relative to our initial 45 degree angular displacement. Okay, so now for the pendulum, it's a little more complicated, but it's simple when you break it up into parts. So you break it up into one part, which is just the big circle, That's one part. And then the second part is the pendulum. And then you can add the big circle plus the pendulum motions together in like a superposition. Okay, so let's start with the x coordinate. So, right, so what is this length here? Oh, it's the same as the other. It's going to be r sine 45, right, initially. And it's going to be, notice we're also to the right of the origin, so that we're going to have a positive r sine 45. But notice that if we increase theta to 45, then the pendulum is going to go up here, right? And if you notice, the x position increased. We went in the positive x coordinate. How will we get that? Well, if we have 45 plus 45, 45 plus 45 is 90. Sine of 90 is 1, which gives us a positive r, right? Which is what we want, right? Because this distance here, that is a positive r. Okay, so that's going to be positive. Okay, but then there's the other part, the pendulum part. Right, so I'm going to draw a little triangle. Let's say the pendulum increased by a positive theta. You can choose it to be going to the left, in which case you'll have a negative theta. Make sure to keep track of that. So the lengths of these sides are going to be root 2r sine of alpha, and then this guy is root 2r times cosine of alpha. Okay, so we're talking about the horizontal position, so we're looking at this guy first. How does this fit in? Are we going to be adding it, subtracting it? Well, we're going to be adding it. Root 2r sine of alpha. So why is that? That's because as alpha increases, then the pendulum will move into the positive x direction, which is towards the right. And so we need to add it. Yeah, so the y coordinates. So let's start with the big circle. Right, so the magnitude is going to be r cos 45, and we're again below the y-axis. So we're going to have a minus r cosine of 45 plus or minus theta. Actually, before I do that, let's do the pendulum part, because it might make more sense to get the signs right. So for the pendulum, we're going to have a root 2r cosine alpha, and it's going to be minus, right, because the pendulum is going down, right? So when theta is equal to 45, right, only the pendulum is contributing to the y position of m2, right? If we draw this here, this magnitude below the y-axis, that's all due to the length of the pendulum. So then that means that we want this this to turn out to be 0 when theta is equal to 45, right? And that only happens when we have 45 plus 45, because cos of 90 is 0. So we have 45 plus theta. And if you're unsure about this part here, then let's do put in some values. So when theta is equal to 0, and let's say alpha is also 0, then we'll have negative r cosine of 45 minus root 2r cosine of 0. Oops, 0. So that's going to equal negative r root 2 over 2 minus root 2 times r. So that's going to be equal to negative 3 root 2 r over 2. So is that correct? Well, let's check this out. So the length initially is going to be r cosine 45, right, because that's this length here, plus just the length of the pendulum, root 2r. I'm doing minus because we're below the x-axis. So what's that equal to? That's negative r root 2 over 2 minus root 2r, which is again negative 3 root 2r. And then if you plug in theta is equal to 45 and alpha is equal to 0, then you'll also get, you should get root 2r, negative root 2r. Okay, so that's really the only physicsy part. This is math. So let's do, so if we have our Lagrangian, t minus v, then we know we want velocities, because t is equal to 1/2 m v squared for every particle. Okay, so let's start with v1. Well, this one's kind of easy. I mean, you could just take the derivative of r1, right? The first time derivative of r1. But you can just notice that m is just in a circular motion about a radius r, and so that's just going to be r squared times omega squared. And just because we're doing Lagrangians, we want to write this out explicitly in terms of theta, right? So omega, the angular velocity is omega dot, or the time derivative of theta squared. Hopefully you know this. You can just show it just through this. Take the derivative of this guy. It's really easy. Okay, a v2 squared. This is a little more involved. So v2 squared is going to be equal to v2x squared plus v2y squared. Right. That's just standard formula for vectors. So that's going to be equal to, let's look over here. So we'll have r times cosine of 45 plus theta times theta dot, because of the chain rule, plus root 2 r cosine alpha times alpha dot. And that's going to be squared, plus, let's see, we have a derivative of cosine is negative sign, so we got, it'll cancel with that minus sign, so we'll have r sine 45 plus theta times theta dot. And then again, the minuses will cancel, and we'll have plus root 2r sine of alpha dot squared. Running out of room. Okay, actually, I should have changed pens, huh? Whatever, it's too late now. Okay, so this is going to be equal to r squared cosine squared times theta dot squared plus 2 times root 2 r squared cosine of 45 plus theta cosine of alpha dot plus 2 r squared cosine squared of alpha dot squared. And I'm going to go to the next line, continue this. So we're doing this guy now. R squared sine squared of 45 plus theta dot squared plus 2 root 2 r squared. Let's see, bring these out first. Theta dot alpha dot sine of 45 plus theta sine of alpha. Oh, and one more. 2 r squared sine squared of alpha dot squared. Oof, what a doozy. Okay. So what are we going to do about this? Well, remember cosine of anything plus sine of that same thing is 1. So that means that these two guys we can simplify, and what else? These two guys we can also simplify. So we're going to have, if we factor out an r squared theta dot squared, we'll just have a cosine squared plus sine squared, so that's just 1. So those are gone. And then for the other guys, it's going to be 2. We factor out a 2r squared alpha dot squared. Okay, and then we have plus 2 root 2 r squared. Is there, am I missing something? Hold on. Oh dear. This is theta dot. Yeah, okay. Yeah, so these should be good. So we can we can also factor out like terms here. Theta dot alpha dot cosine of 45 plus theta times cosine of alpha plus sine of 45 plus theta sine of alpha. So this just screams out trig identities, right? What if you don't remember them? Oh, you can just use Euler's formula. I like to use that. So we're going to do that just to show you, in case you're unaware. We have e to the I theta is equal to cosine theta plus I sine theta. Okay, so how does that help us? Well, if we say take e to the I of, let's call it beta plus kappa is equal to e to the I beta, e to the I kappa, it's kappa. This is equal to cosine of beta plus kappa plus I sine of beta plus kappa. Oh, actually, you know what? Let's do minus. Yeah. Beta minus kappa. Beta minus kappa. Well, this is also equal to cosine of beta plus I sine of beta multiplied by cosine of negative kappa, but cosine is even, so cosine of negative kappa is cosine of kappa. And then we'll have sine of negative kappa. Sine is odd, so we can bring the minus sign out. It's minus I sine of kappa. So let's carry out this product. So we have cosine beta, cosine kappa, minus cosine beta, I sine kappa, plus I sine beta, cosine kappa. And then we'll have an I squared, which is -1, which will cancel the minus. We'll have a plus sine squared. Oops, no, not sine squared. Just a plus sine beta sine kappa. Sorry, it's kind of squished. So what do we do here? So we're going to equate this line with this line, where we equate the real parts of one is equal to the real part of the other. So the real part of the top line is cosine of beta minus kappa. The real part of the bottom line is cosine of beta cosine of kappa plus sine of beta sine of kappa. Now what if we let beta equal 45 plus theta, kappa is equal to alpha, then we get cosine of 45 plus theta minus alpha is equal to cosine of, well, you get the picture. We can substitute this for cosine of 45 plus theta minus alpha. Let's write down a Lagrangian, because the potential is pretty easy. We can just do it on the fly. So we're going to have a 1/2 m times v1 squared plus v2 squared. So v1 squared is r squared theta dot squared, right? v2 squared is this line. So we'll have, another r squared theta dot squared. So we'll have two of these right there. And then a 2r squared alpha dot squared. Okay, that's the kinetic. So now what's the potential? So it's all gravitational, right? And we're going to have the gravitational potential onto the mass 1 and then onto mass 2. So let's write it down here. So we have minus mg, let's start with here, mass 1. So mass of m times its vertical displacement, which we know to be this guy right here, minus r, cosine 45 minus theta. Okay, let's put a bracket there. Okay, and then for the pendulum, we have this guy. Okay, so we'll have a plus mg times negative r cosine 45 plus theta minus root 2r cosine of alpha. Let's do some simplifications. That's the Lagrangian. Pat yourself on the back. At this point, we can diverge. So we can either make the approximation that we're doing small oscillations before we plug into the Euler-Lagrange equations, or we can do the approximation afterwards. Doing it afterwards is really painful. So we're going to do it before. But I did it both ways, and you get the same answer. Here, we're going to approximate to second order. So what does that mean? That means that cosine of something is going to be 1 minus that something squared over 2, and sine of that something will be x, right? Because the next term in the Taylor series of sine is x to the third over 3 factorial, but we don't care about that. Okay, and then similarly, anything that has, so therefore, the Lagrangian is going to be, let's see, mr squared. Okay, theta dot, that can stay. Alpha dot squared, right, because we're taking a second order. So this is also theta dot times alpha dot, that is second order. Since theta and alpha are going to be so small, they're going to be negligible compared to 45. So this is going to be approximately, or very much equal to cosine of 45, which is equal to root 2 over 2, which cancels. Okay. Okay, let's continue. So we have mgr cosines plus cosines. Well, this is actually another trig identity. Wouldn't you know it? You can actually derive it using Euler's identity again. But this time you have to use the exponential representation of cosine, which is 1/2 e to the ix plus e to the minus ix. You can prove this easily using that, but I'm just going to cite it here that cosine of 45 minus theta plus cosine of 45 plus theta is equal to 2 times cosine of 45, which is root 2 over 2, times cosine of theta. These cancel. Okay, so we have mgr times root 2 cosine theta. Oh, well, remember cosine theta is actually 1 minus theta squared over 2 plus root 2 times another 1 minus alpha squared over 2. So I can write that better. There you go. Let's simplify this part here, or actually just the inside part here. So we'll have root 2 plus another root 2, so that's 2 root 2, and then a minus root 2 over 2 theta squared minus a root 2 over 2 alpha squared. So in total we'll get this mgr 2 root 2 minus an mgr. This guy here is just a constant, and when we use our Euler-Lagrange equations, we're going to be taking derivatives of everything. So we can just forget about it. So the Lagrangian is actually this. Okay, so now we have 2 coordinates, so that means that we need to apply the Euler-Lagrange equations to, or apply it twice. So what are they? We have d by dt of the partial of the Lagrangian with respect to, let's start with theta. Theta dot, our generalized momentum, and that's going to be equal to the partial of the Lagrangian with respect to theta, d by dt of mr squared times 2 theta dot plus alpha dot. And is there anything else with respect to theta dot? No, there isn't. So we're done with that. That's going to be equal to, let's look for anything theta related. So that's it. So we're going to have minus mgr over 2 root 2 times theta. We'll take the time derivative, so we'll have mr squared 2 theta double dot plus alpha double dot. So this is negative root 2 mg r theta. We can cancel the m's and one of the r's, so we can get, awesome, we got an equation of motion. Alright, next up. Also, if you're unfamiliar with the Euler-Lagrange equations, you could read the textbook. Or I could make a video trying to explain it, I guess. That could be fun. Okay. Oh my gosh, I'm on autopilot. This is alpha dot, and that's alpha. Okay. So we'll have a mr squared 2 alpha dot plus theta dot. That's it. Okay. And then on the right side, all we have is this guy here. So we'll have a minus mgr over root 2 times 2 alpha. Take the time derivative, mr squared times 2 alpha double dot plus theta double dot. Again, we'll have root 2, and then the m and the r's will cancel, so we'll have g alpha. Okay. So we need to find the normal modes. Right, and if you need a refresher, the normal modes are the pure frequencies of relative motion between the two masses. So if we have mass 1 going this way, then the pendulum could also be going this way, right? And then as the mass goes back this way, then the pendulum will go back this way. That's one mode where they go in sync with each other. And then another mode is if M1 is going in and M2 is going, or M1 is going to the right and M2 is going to the left. So that's another normal mode. And then the chaotic behavior that you see of the two objects is actually just this a combination of those two frequencies. So how do we do this? I like to do it the surefire way. It doesn't require any weird inspiration. You just let theta, just let theta and alpha, I'm going to write this in vector notation. So A and B are complex constants, and then omega is going to be our frequency, and then I, in case things become complex, which they will. Okay, so what does this mean? That means that theta dot alpha dot is equal to omega, or I omega, AB e to the I omega t, and theta double dot alpha double dot is equal to I squared, which is negative omega squared AB 2r theta double dot, so that's minus omega squared A e to the I omega t plus r times alpha double dot, which is negative omega squared b e to the I omega t. This equals negative root 2 theta, which is a e I to the omega t times g. So we divide by e to the positive I omega t, right, to get rid of all the exponents. And we can just do that in one step here. And of course we can do this because e is never equal to 0, except in the limit to negative infinity. Okay, so what do we do with this? Well, we can put this in matrix notation and have it as a matrix times a vector where the vector is AB. Actually, before we do that, I should write everything to one side. Okay, and then we'll have the 0 vector on the right side. So we multiply A by negative 2r omega squared plus root 2g, and then B times negative r omega squared. This one was going to be negative r omega squared, and this one is negative 2r omega squared plus root 2g. Right, because you do multiply this by this plus this times this, and that equals the top 0 and then the other guy. So this is the same thing, but now we can use our linear algebra knowledge and say that A and B, we want that to be a non-trivial solution, because if they're 0, then that just means theta and alpha are 0, which is not a solution. And that means that we want this matrix to be non-singular, and for that to be the case, we want the reason for that is because we don't want it to be invertible, so we want it to be non-singular. So let's take the determinant of this matrix. So remember it's this times that minus this times that, which equals 4 r squared omega to the 4th minus 2 root 2 r omega squared g minus plus 2g squared. We have 3 negatives here, so it's going to be minus r squared omega to the 4th, which equals 0. Alright, so let's combine like terms. So omega to the 4th, we have 4r squared minus r squared, that's 3r squared omega to the 4th minus 4 root 2 rg omega squared plus 2g squared. And this might not look like it, but it's actually a quadratic polynomial in terms of omega squared, right? If we just rewrite this as omega squared squared, and this is just omega squared, we can use the quadratic formula on omega squared. And before we use the quadratic formula, I'm going to divide everything by 3 to the r squared, just because I feel like it. We'll have 4 root 2 over 3r g omega squared plus 2/3 g squared over r squared equals 0. Okay. Omega squared is going to be equal to 4 root 2 3 over r g plus or minus the square root of 16 times 2 times g squared all over 9 times r squared minus 4 times 2 times g squared over 3r squared all over 2. So let's simplify this by bringing the 2 inside the radical, which case is going to be, right, 1 over 2 is equal to square root of 1 over 4, so we can bring that inside the square root. For this guy, it's going to be 2 root 2g over 3r plus or minus the square root of times 2 over 9 g squared r squared minus 2/3 r squared g squared. Let's multiply this by 3, this by 3. So that will give us, right, 8 minus 6. So that's 2 g squared over 9r squared square root. So this ends up being 2 root 2g over 3r plus or minus the square root of 2g over 3r. If we add them, we get 3 root 2g over 3r. If we subtract them, then we get root 2g over 3r. That's almost the answer, except remember that's omega squared. That means that omega, our frequency for our normal modes, is going to be square root of 2g over r. Right, when we take this square root, we get 2 solutions here. So in total we get 4 solutions. Pretty cool. These are going to be the frequency of our normal modes. So how do we find them? Well, we have to plug them into our matrix equation here and see what we get for a and b. Let's say omega is equal to square root of root 2g over r. Then, okay, so we're going to get a times this, I'm just going to call it star, a times star minus r root 2g, oh, this we can go away with, times b, negative root 2g a plus b times star. It's also equal to 0. So what we want to do at this point is solve for the ratio of a over b. We can't actually solve for a and b themselves. That's because they're coupled to each other. If I say a b is equal to root 2g a over star, that means that b over a is equal to, so this is equal to negative root 2g. Yeah, so this is equal to negative 1. So that means that a is equal to negative b. And that is going to be one of our normal modes. Okay, So that means that our normal coordinates, x minus y, which is the same thing as the normal mode, which you can write in vector notation as 1, negative 1. We have the frequency square root of the square root of 2 times g over r. We know that this guy here, the negative out in front, will also give us the same normal mode. And if you plug in omega is equal to the square root of root 2g over 3r, then you can do the math. You'll get b is equal to a. Our normal coordinates are x plus y. The normal mode is this vector 1, 1. Okay, so how do we write our solutions? We have theta and alpha of t. And I'm going to write it in vector notation. So we're going to have a superposition of two normal modes. So we write it like this. Start with 1, 1. So it's going to have e to the, by the way, I'm going to call this omega 1. This will be omega 2. So I don't have to keep rewriting that. So it's e to the I omega 1 t plus c2 1, 1 e to the negative I omega 1 t plus c3 1, negative 1 e to the I omega 2 t plus c4 1, negative 1 e to the negative I omega 2 t. Right, and we're doing this, again, this is a superposition of 4 different solutions to our coupled second order differential equations. So now we want to write this in terms of real variables, because theta and alpha are real. So how do we do that? Well, the omega 1, the positive and negative, come in conjugate pairs. So that means that C1 is equal to C2 conjugate. So if C1 is equal to, let's give it, what letter do we want? Delta. Yeah. Delta times e to the I phi. Then that means that C2 is equal to delta times e to the negative I phi 1. And similarly, C3 is equal to C4 conjugate. So we'll have C3 is equal to epsilon e to the negative I phi 2. Where these phi's are just arbitrary phase constants. Okay, so we can plug all this in and then use Euler's formula to get things in terms of real variables. I'm going to group the exponents together. So we'll have an I times omega 1 t plus phi 1 plus 1, 1 delta e to the negative I omega 1 t plus phi 1 negative 1 epsilon e to the wait, I meant this should be positive, yeah, e to the I, so that means that C4 is epsilon e to the negative I phi 2. Okay, so we have omega 2t plus phi 2 and the same thing, running out of space, omega t plus phi 2, oh gosh. It's going to be a long ass video. Okay, Euler's formula. I feel like my handwriting is getting worse and worse. Okay, so this and that cancel, this and that cancel. So we'll get 1, 1 delta times 2, which we can just bring inside the delta. So we'll call this delta prime now, times cosine of omega 1 t plus phi 1 plus 1, negative 1, epsilon prime. That sounds like a planet, like a science fiction movie. But it is, epsilon prime. Oops, this should be phi 2. That's it. When theta is equal to alpha, then this will cancel out because there is no dependence of theta plus alpha on cosine of omega 2t plus phi. Whereas if theta is equal to negative alpha, then this term will vanish because there's no dependency of theta minus alpha on cosine of omega 1t plus phi 1. Okay?